Hi, Assalamualaikum. Good morning. We meet again for my third recorded lecture for CHM676. If you can recall, that my second recorded lecture was on electron counting, how to count the electrons for your organometallic compounds. So I hope you have done some practice exercises after my lecture, so that you can become familiar with what we learned last time. Now, if you can recall, 18 electron count, the count of 18 electron is uh, important because that will determine whether your compound is stable or not. If your compound has 18 electrons, it is very, very likely to be stable. And if it has less than 18 electrons or more than 18 electrons, then that compound is very much likely to be unstable. However, for every rule, there is always an exception to the rule. So the 18 electrons rule are only strictly followed by the metals or the transition metals located in the middle of the series. Why are the ones in the middle of the series obeying the 18 electrons? 18 electron rules, because they have the suitable size and the suitable energy to do so. This is the 10 transition metals. Well, here you have 2, 4, 6, 8. Copper and zinc. Yeah, copper and zinc are at the on the right hand side here, not seen for now. So you have the middle transition metals, which will strictly follow the 18 electron rules. You're going to have the early transition metals in the first series. You have scandium, titanium, or vanadium. They will have difficulty in obeying the 18 electron rule for for what we call static factor. I'm going to explain to you static factor in a while. And the late transition series, for example, cobalt, nickel, copper, and zinc, the ones that are not shown at the, two more columns on the right, they are also having some problem in obeying the 18 electron rule. But this one, for the late transition series, the reason for disobeying is because of energy factor. Now let's go through the static factor and the energy factor so that you can understand it fully. There are exceptions to 18 electron rule. Yep. There are exceptions to 18 electron rules, and there are two reasons for breaking of the 18 electron rule. The first reason is for transition metals early in the series, such as titanium and vanadium. Now, early transition metal series are small in size, yeah? Small in size. So they have difficulty in terms of static hindrance. What do I mean by static hindrance? Static hindrance means limitation in terms of space. When we talk about static, it is always space, yeah? Concern of space. Static hindrance limit the ability of metal centers to accommodate the number of ligands required to supply 18 electrons. So stable compounds of these metals containing 16 valence shell electrons can be found. I'm going to give you some example. I'm going to add, just bear with me for a while. Okay, now I have added an example down here where you can copy this down, or you can write this down because it is not in your notes. I've just recently added it. So for example, if you are to consider a compound, an organometallic compound, TiCOX, where X is unknown, I would want to ask for you to determine the value of X, or how that means how many carbonyl is required to obey 18 electron rule, and then predict. This should be from, not form, and from. And from that value, predict if the compound is going to be able to accommodate all the required CO ligands to achieve 18 electrons. Yep, to achieve 18 electrons. Okay, how are you going to do that? It's really very simple. You've learned this before in the previous lecture. The table of fragment, charge, and electrons is very, very important. The first fragment that you see for this compound, TiCO6, is the titanium 0. Why do I know it is 0? Because the carbonyl has no charge. So if the carbonyl doesn't carry with it any charge, and the total compound doesn't have any charge on it as well, as we can see here, so obviously your titanium is going to be titanium 0. And titanium 0, it is on the fourth column in the periodic table. So you have 4 electrons for titanium 0. How many number of carbon monoxide is required? You don't know yet. So you put X times 2. 2 for each carbon monoxide, and the total number of electrons required to achieve 18 electron is obviously 18. So we do simple mathematics here. 2x plus 4, 2x plus 4 is equal 18. 2x is 14 and x is 7. So the compound requires 7 carbon monoxide ligands to obey the 18 electron rule. Now 7 is far too many. Usually for reason of space, a metal like titanium, a small metal like titanium, will have a maximum number of 6 ligands to attach to itself. More than 6 is just going to be too many. So it's too many ligands to crowd around the titanium metal center. So if you consider this titanium, and it has to put 7 ligands, 7 CO ligands around it, the repulsion between the 7 ligands will be too high. Yeah, will be too high, so that the repulsion will destabilize that compound, and destabilization due to repulsion of the 7 ligands around titanium is going to make that compound unstable anyway. So it is a toss between wanting to achieve 18 electrons but yet too crowded, or not achieving 18 electrons but still remaining quite comfortable in terms of space. So for TiCO, they usually would go for 1 less carbon monoxide. So usually it's going to only have 6 carbon monoxide around it, but if you make 6, this is going to be 16, yeah, because if that is 6, this is going to be 12. 12 plus 4 is 16. So titanium will usually settle for a number of electron less than 18 because of the steric factor, yeah, because of the space factor. So that is the reason why elements in the early transition metal would tend to break the 18 electron rule. Is that clear? Now, the second way that transition metals disobey 18 electron rule is by due to the energy factor. If the early transition metal was due to the steric factor, for the late transition metals, the Disobeying of the 18 electron rule is due to the energy factor. Now let's read this together. For metals late in the series, such as copper and zinc, it is common to find only 16 valence shell electrons. This is because for these metals, the 3d orbitals have very low energy. They become part of the atomic core and too stable to participate in bonding. So look at this diagram below, right? Right here. Now, if you look at the energy of the 4s orbital as you move from calcium to zinc, in the same series, you're going to see that the energy of the 4s orbital goes down as we move across the periodic table. Similarly, with the energy of the 4p orbital goes down quite slowly as we go across the periodic table. But looking at the 3d orbital, it also goes down in energy as you move from your left to the right of your periodic table. But the rate of reduction of this energy is far too steep. Yeah, the slope of the reduction of the energy of the 3d orbital is too steep. Even before it reaches the end of the series, the 3d orbitals already become a very my alarm goes off. Already has very low energy that it goes into the inner atomic core. That means it goes into the second shell, because if you recall, the 3D is obviously in the third shell. But when the energy of the 3D orbitals reaches copper and zinc, these have energy very, very low. It goes into the region of the second shell. So these become very, very inert, very, very stable, and they do not want to participate in bonding for copper and zinc. So because of that, figure 1, I'm sorry, it's just, yeah, I'm going to have to do this. Yep. The change in energy of the 3D, 4s, and 4p orbitals of the first transition series is shown above. And you can see that 3D dips very, very steeply into the atomic core. So in terms of energy, all the orbitals become more stable. More stable means have lower energy as the effective nuclear charge increases across the series. As the end of the series approach, the 3D and 4s orbitals drop in energy faster than the 4p until nickel, where the 3D orbitals become part of the atomic core and too stable to participate in bonding. So when they become too stable to participate in bonding, they're just not going to make a bond. When they're not going to make a bond, that means these late transition metals, including the copper and zinc at the end, are going to only have energy enough to make 16 electrons, not 18. And they can be stable. Similarly with the first one here, even if it only has 16 electrons, they can be stable due to the steric factor. For the late transition metal, even if they have 16 or less than 18 electrons, they can also be stable due to energy factor because of this factor that I was explaining to you earlier. I hope that is clear, the two reasons why 18 electron rules cannot be obeyed by transition metals in the early series and in the late series. Yep. Okay, I'm going to go next into 16 electron species. Yeah, this is 16 electron species is a typical number when a compound disobey 18 electron rule. Now, most stable organometallic compounds obey the 18 electron rule. However, stable complexes do exist with electron counts other than 18. As factors such as crystal field stabilization energy, you have learned about this CFSE, and the nature of bonding between metal and ligand has an effect on the stability of the compound. The most widely encountered exception to the rule are the 16 electron complexes of the transition metals on the right-hand side of the D block. That means the late transition metals, particularly group 9 and 10. These 16 electrons, typically square planar complexes most of the time, commonly have D8 electron configuration. For example, rhodium 1, iridium 1, nickel 2, palladium 2. And examples of such complexes include anion of the Zeiss salt. I'm going to talk to you about the Zeiss salt. Oh gosh, the T is not italicized. Okay, I'm going to talk to you about the Zeiss salt, and also I'm going to talk to you about the Vasquez compound. This is the formula for the Zeiss salt, and this is the formula for the Vasquez compound. Later, I'm going to explain it to you. So you have the 16 electron species disobeying the 18 electron species, and yet they are stable due to factors such as the energy, such as CFSE, such as the nature of bonding. Another thing that is the way that compounds disobey 18 electron rule is by having odd electron species. You have met odd electron species last week when we did exercise on VCO 6 minus, VCO 6. Odd electron complexes may achieve stability by accepting an electron. Either by accepting an electron to become a negatively charged species, or by dimerization. I'm going to show you dimerization in a while. For example, VCO6 is a 17 electron species. You have worked it out. It readily completes the 18 electron configuration by accepting an electron from a reducing agent. So by accepting an electron, VCO6 will become VCO6 minus, and the 17 electron will become 18 electron. And achieving the 18 electron will increase the stability of that species. Other odd electron species may acquire another electron through dimerization. Now, dimerization means make two with another molecule. For example, when you count the electrons for MnCO5, now CO5 has 10 electrons, 5 times 2. Manganese 0 is 7 in the 7th column, so it has 7 electrons. So this is a 17 electron species. When two of these 17 electron species share their odd electron, they can form another extra bond, which is a manganese to manganese bond. So consequently, when two of these make a manganese to manganese bond, there is an extra bond here where the odd electron, the one unpaired electron, will pair up, and consequently they become 18 electron species. I'm going to add another picture down here so that becomes clear. Just bear with me in a while. Right, I have added another example down here, which you probably would like to copy as well. Now, the dimerization of MnCO5, two of these will dimerize to make manganese to manganese bond, connecting the two manganese centers. This one's here. If you count the electrons for this MnCO5, you're going to find that it is unstable. It is less than 18. is less than 18, so it is unstable. But upon dimerization, you have 2 manganese centers, 10 carbon monoxide, and 1 additional manganese to manganese bond, which is not present in here. So you have 2 manganese, 0 is 2 times 7, 14. 10 CO is 10 times 2, 20. Manganese to manganese, a bond between 2 metals, that the one that I was teaching you about in my lecture, recorded lecture 2, is 2 electrons. So adding up 14, 20, and 2 gives you 36. So for each manganese, the number of valence electrons is 36 divided by 2, it is 18. Therefore, Mn2CO10, the dimerized product, is stable. Yep. So either it receives 1 electrons to become 18 electron species, or it can dimerize as well to achieve stability. So that is a prelude to this little topic, metal-to-metal bonding and the 18 electron rule. The 18 electron rule can be useful in predicting the number of metal-to-metal bonds in an organometallic compound which contains multiple metal atoms. Such a molecule will be most stable if the number of electrons around each metal atom is 18. As we have seen examples discussed above, the metal may gain additional electrons by forming covalent bonds to another metal atom. This is another example. You have molybdenum bonded with 3 carbon monoxide, and this is an olefin ligand which we call cyclopentadienyl. I'm going to introduce cyclopentadienyl to you in maybe about 5 lectures time. So just enough sufficient for you to know for now that cyclopentadienyl carries with it a 1 negative charge and 6 electrons. So let's carry this to the next page so you can see the whole picture. So the cyclopentadienyl, molybdenum, carbon monoxide 3 dimerized. So how do we count electrons for that dimer? So again, if we go for each molybdenum, remember, each molybdenum, this is the picture. This is your molybdenum with your cyclopentadienyl. This is your cyclopentadienyl, 3 carbon monoxide, and a molybdenum 2 molybdenum bond. If you only take half of that molecule, let's do this. Let's break this molecule into 2. It should be dashes like that, and I would like a red color. Okay. Breaking this dimer into 2 when we do electron count is very useful as well. At least you do not have to divide it by 2 like this one here. This is when you do a whole molecule, this calculation at the top. Now, for each molybdenum, the molybdenum, first of all, you do not know what is the charge of this molybdenum. I'm just going to make it blue there because you do not know yet what is the charge and what is the electron for to start with. How you are going to determine the charges simply by looking at what other charges are carried by the ligands. For example, I told you that your cyclopentadienyl is a -1 carrier with 6 electron donor. Your 3 carbon monoxide has 0 charge with 6 electrons. That means 2 times 3. And not 2 of half, it is half. Half of molybdenum 2 molybdenum. This is 1 MO to MO. You make that half. So half of bridging. Mu means bridging, bridging molybdenum to molybdenum. So it is actually half, excuse me, this is getting a little bit, oh, undo, let's do this. All right, let's do that. Copy, you please correct your notes, yeah? Half of 2. Half of 2 is 1. Just excuse this typing a little bit. Just like that. Yep. Half of 2, the charge, obviously, the charge for, oops, the charge for metal to metal bond is 0. Yep. So charge for metal to metal bond is 0. Half of 2 bond is 1. So for you to determine what is the charge of your molybdenum, you must look at this minus 1 plus 0 plus 0 plus x, for now this is x, is equal to 0. So x must be plus 1. So when x is plus 1, so your molybdenum is molybdenum 1. When your molybdenum is molybdenum 1, the number of d electrons that it carries is 6, which is when it is 0, when its oxidation state is 0. 6 minus 1 becomes 5. So you have 5 electrons from molybdenum 1, 6 electrons from your cyclopentadienyl, 6 electrons from your 3 carbon monoxide, and 1 electron from this, half of molybdenum to molybdenum. In total, you get 18 electrons. Yep. So when each molybdenum has 18 electrons, then it is stable. If you do the same count, it is going to be the same on the left side or on the right side of that molecule. So as a note, the number of metal is the oxidation number of metal is found to be plus 1 to counter the minus 1 charge of the cyclopentadienyl. Without the molybdenum to molybdenum bond, 1 unit of this only has 17 electron. It easily fulfills the 18 electron rule by dimerizing with another unit through 1 MO-MO bond. If forming 1 metal single bond is not sufficient to make 18, the metal to metal double bond can be formed. Yeah, so that is how it is counted. So maybe one of the questions that I gave you from the past year's paper, you can tackle it now using the knowledge that you gain from this lecture. So for now, I'm going to stop my lecture, recorded lecture 3, and next we're going to see about the other ligands other than the carbon monoxide ligand. We're going to go into phosphines and others. So hoping that you have understood the lecture very well, and please ask me any question in the forum if you have any problem. So that's it for now. Assalamualaikum, and have a good week ahead of you. Bye.